What's going on, everybody? My name is Mr. Smith, and welcome to another issue of Physical Science at Home. Here's what we're doing today. We're going to be talking about waves, we're going to be talking about formulas and equations. Today is a math day, so get excited. However, if you stay tuned, I will show you how musical instruments work. So get excited for that. Let's get going. All right, so here's a picture of a wave. We've seen this before. What I'm going to do here is I'm just going to label this lambda 1 as with a value of 1. So when you see that little wavelength sign, remember that's lambda, and then the little sub 1 there is just saying this is a wavelength. It's got a value of 1 meter, something like that. What you'll notice here is that I have 4 wavelengths, just because you can see it goes up and down and then comes back to 0. That's 1 wavelength, up and down a second time, a third time, and a fourth time. That gives me a total of 4 wavelengths here. So you'll notice that the x-axis is time. So for this wavelength, what I want you to do is tell me, what is the frequency? Do you remember how to find that? What is the frequency? That's the question. Pause it if you're not ready. The answer here is frequency is 4 hertz, meaning that since I complete 4 wavelengths over the course of 1 second, I have a frequency of 4 hertz. Remember, hertz, Hz, that is the number of wavelengths per second. So this can also be written as 1 divided by seconds if you wanted to write that as a unit instead of hertz. What we're talking about here is a trend. So as wavelength increases, we want to know what happens to frequency. So what I'm going to show you on the next slide is now my wavelength will be double the length. We're going to call that lambda 2. Oh, remember here, wavelength is distance between 2 equally high points, and frequency is the number of waves per second. So those are good definitions to know. And know that the unit for wavelength is meters, and the unit for frequency is hertz, or 1 divided by second. Those two things are the same thing. Okay, lambda is going to get doubled here, so now you'll see in this next picture, notice the wave is a lot wider, still in that time, 1 second. So now we'll say lambda 2, that's going to equal 2, just giving it a value of 2 meters. And you'll see that it takes 2 wavelengths to kind of cover that 1 second period. So what we're going to notice here is that as wavelength increases, our frequency is going to decrease. Here, since we have 2 wavelengths per second, our frequency is now 2 hertz. So it went from 4 hertz down to 2 hertz. So our frequency has decreased. There's the definitions for wavelength and frequency there. So the trend here is as wavelength increases, frequency decreases. We can also flip that around. That's if we're going from top to bottom here. As our wavelength is increasing, our frequency is slowing down. It goes from 4 hertz to 2 hertz as our wavelength goes from 1 to 2. But like I said, we can flip that around. So if I'm looking at frequency going from 2 hertz all the way up to 4 hertz, in that time, my wavelength is decreasing by a factor of 1, or 2, I guess it's halving. So yeah, they're oppositely related to each other. If one goes up, wavelength goes up, frequency has to go down. If frequency goes up, wavelength has to go down. Because the longer your wave is, the less number of waves you can fit in a 1 second time frame. That's kind of the rationale there. Okay, so with this idea of wavelength and frequency and the relationship, some dude back in the day came up with an equation. The equation is for the speed of a wave. So it turns out that velocity is if you take the wavelength and then you multiply it by the frequency. So you take how long the wave is, and you take how many waves you have per second, and you're going to end up getting a speed, which makes sense. This wavelength unit is meters, and this frequency unit is hertz, which is the same thing as 1 divided by second. So if you take meters, you multiply it by 1 divided by second, you're going to get meters per second, which, remember, is the unit for velocity, meters per second. Also remember, wavelength here in green, that's abbreviated with a lambda, which looks like an upside down Y. Frequency is abbreviated with an F, and velocity is abbreviated with a V. So what we're going to do is the same thing we've been doing with a lot of equations that look very similar to this. We're going to give you a word problem. We're going to give you 2 of these variables in the word problem. You have to figure out where to put them and how to solve them. So let's go ahead and start with an example problem that we'll do together. It says, if a wave has a wavelength of 0.005 meters and a frequency of 200,000 hertz, what is the speed of the wave? Okay, so we're going to use that equation, V equals lambda times F. So I'm going to write that down first. Always write your equation first. Then I'm going to look to plug in things from the problem. So I'm going to box these guys in the problem. First thing we notice in green here is that meter. It says wavelength of, so we know that that's going to be our lambda value there, boxed out in green. In blue, we're going to box that 20,000 hertz. It says frequency of 20,000, and it's got that hertz, that 1/2 variable or unit. So we're going to know that that's going to be replaced by F. What is the speed of the wave? That's the question we're trying to answer, so this V is going to stay as a V. All we have to do now is plug in these numbers, which you'll see I do in the next one, where I'm multiplying these two numbers together, and then I get my final answer of 1,000 meters per second, which, in case you were wondering, 1,000 meters per second is about twice the speed of sound. Actually, maybe closer to 3 times the speed of sound. So yeah, fun facts. Here's another speed of the wave problem. Once again, we're going to use these equations right below here, and here are the units. I replaced 1 divided by second with hertz. It means the same thing. Here's the example problem. Go ahead and take a moment, pause the video, and try and solve this out. It's about sound, so get excited for that. Great, hopefully you got a chance to try this problem out. We're going to go over it together. So in this problem, what's different here is that we've been given the V, the velocity, 343 meters per second. That's the speed of sound. And we've been given the frequency. So we're looking for wavelength here. We're looking for that green variable that we're going to try and plug in. So what we have to do is first plug in the variables. And then now in order to solve this, we've got to isolate wavelength. How we're going to do that is we're going to divide both sides by that 261.6 number, which was the frequency of a middle C. And then when we do that, we end up getting a 1.31 meters. So yeah, it turns out that if you take a sound wave, its frequency is about 1.31 meters, which is roughly, I'd say, 4 feet. So kind of crazy that there's sound waves out there that have 4 feet wavelengths. But you can't see them. Kind of crazy. Okay, so that is speed of a wave. Expect some problems coming up with those. What I wanted to talk about now is I wanted to talk about sound, just because we got into it. It turns out that a high frequency, that would also give you a short wavelength, because remember, as frequency increases, wavelength has to decrease, and vice versa. But a high frequency is what creates a high pitch. So if we had two sound waves here, the top one in green, that would have a higher pitch than the bottom one. The bottom one would have a lower pitch just because it's got a longer wavelength and also a shorter frequency. Or sorry, it's got a higher, the high pitch one has a high frequency and a shorter wavelength. Okay, now something that was interesting to me is as I was looking it up, I found out a ton about how sound gets produced. So this isn't necessarily super important to know, but I thought maybe you'd like to know it. It turns out that when it comes to strings, strings actually vibrate. So they create these little transverse waves where they're going up and down. And those transverse waves then vibrate the air. And that vibrates the air in a more longitudinal way, where you get compressions and rarefactions and compressions. It turns out the thicker the string, the lower the sound. It's also based on length as well. So like, for example, a bass versus a violin. A bass has a lot longer strings, but the strings are also thicker. That's why it produces a lower sound. And also, if you loosen a string, it will produce a lower sound. And then the opposite is true for high strings. The shorter, thinner, and higher the tension is. The reason why that is, longer, thicker, and lower tension strings is because they will produce longer wavelengths. If you have a thick string, it'll move more air, kind of producing a longer wavelength. If it's longer, it's going to, again, move more air. And if it's thicker, or if it's lower tension, it's going to move that air more slowly, again, creating a lower sound. Also, if you read that last bullet point, you don't have air in space, so you can't make sound, because sound has to have a medium to travel through, like air. or even water. Sometimes you can hear things underwater just because it's compressing water. So yeah, fun fact. Here's how brass works. I found this super interesting. It turns out that with brass instruments, they have that little mouthpiece. And in the mouthpiece, they can kind of produce a short range of sounds. But then a trumpet, if you'll see down here in this diagram that I drew, a trumpet's got 3 different tubes that, depending on which combination of taps you press, allow the air to be either a certain distance. So if you press the first one, it's a middle-sized distance. The second one, it's a medium distance. And the third one, it's a long distance. So if you want to make a low noise, you would press down on that last tap and it would produce a long sound. And I think as well, if you press on a combination of them, it kind of changes. There's a lot of different combinations you can make. Someone who's a trumpet player could probably tell me better. I don't really fully understand it. But kind of the same general idea here is that a long tube will produce a low frequency and a low pitch, because it's got that long wavelength, because that sound can travel a longer distance. Whereas a short tube will have a short wavelength, which means high frequency and, of course, high pitch. So it'll sound like a high note. Woodwinds, kind of interesting. They're just a hollow tube with holes in them. That's all a woodwind is. So if you don't cover any of the holes, you can produce a really high note because it'll kind of escape out of that first hole. Over here, I've shown you kind of the fingering chart for a recorder, I think it is. And you'll notice that the lowest sounds is when you don't blow a whole lot, that's the tiny arrow, and you have all the holes covered. When you have all the holes covered and don't blow a lot, you produce the lowest sound. And then when you have all the holes open and blow very hard, that's when you produce a high sound. It looks like the last one, the D at the very end, they cover all the holes except for the first one. So in that situation, then all the air is going out that first hole. So that's how it produces that super, super high pitch, because everything has a super, super short wavelength. Versus with the C sharp, all the holes are exposed, so it would be kind of a little bit different. You'd have slightly longer wavelengths as well as that really high wavelength. So same rules applies with brass here. A longer tube means a longer wavelength. A shorter tube means a shorter wavelength. Cool. Drums kind of behave like strings. The bigger the drum is, the lower the frequency is, just because a big drum moves more air and can move it slowly, whereas a small drum has less air to move and moves it quickly. Last thing I wanted to show you guys is speakers. This is kind of cool. So it turns out, if you look at number 3 over here, that brown box, that's a permanent magnet. And number 2 over here, that's an electromagnet. So currently with the electromagnet not charged, not having a signal running through it, these guys are just chilling. But as soon as you put a signal through this electromagnet, it polarizes it opposite to the permanent magnet. So then it starts compressing with each other. And those compressions are going to move this cone, generating noise. In general, kind of how the rule is that small cones make high pitches because they compress the air quickly. So those quick compressions are going to generate short wavelengths, which means high frequency, which means high pitch. And then if you have larger cones, you compress the air more slowly, which means low pitch sounds and long wavelength, low frequency type deal. Anyways, I thought that was kind of cool to talk about sound. Hopefully you found that interesting. Hopefully you learned something new today. Thanks again for watching. I hope you guys have a great rest of your day. Take care.